Chapter 1.3 Einstein's interpretation of the photoelectric effect. Hopefully you understand the explanation of photoelectric effect using the particle theory of light. If so, then this will be an easy chapter. This chapter is just a summary of the whole theory that explains the photoelectric effect. First of all, the light particles has a name, photons. So a photon is basically a packet of light energy or a quantum of light energy. The energy of photon is given by hf, where h is called Planck's constant, and that is equal to this number. The unit is joule/second. You know the unit of frequency is hertz, which is per second. So multiplying with the Planck's constant, then you may have the unit joule. From the discussion of the last chapter, you know we are talking about intensity of light. In case we have green light here, and with the same number of photon, but then we change it to red light, then the energy carried by the light will become less, so the intensity decreases. On the other hand, if we change it to violet light with the same number of photon, then there will be more energy carried by the same number of photons, and the intensity increases. On the right hand side, we have the same green light as the middle picture, but then you can see there are more photons here, so the total energy carried by the photons is larger, resulting in higher intensity. Well, what about if the number of photons decreases here? This is still green light, and the energy carried by each photon is the same, but the total energy carried by these photons is less than the energy carried by that number of photons, so the intensity decreases. Simply speaking, intensity increases with the number of photons and also the frequency of light. Example 2 is a simple question. You are given the wavelength. Find the frequency, and then you may find the energy of a photon of red light. And from this example, you can see the energy of photon has an order of -19. It's such a small amount of energy, so we need a smaller unit to measure the energy of photon. And the unit that we are going to use is called electron volt. Simply speaking, 1 electron volt is the energy gained by an electron when it is accelerated by a potential difference of 1 volt, such as in this picture, when the electron is attracted by the higher potential on the right hand side, and the electron becomes faster and faster on the right. So it gains kinetic energy, it gains energy from the electric field. The energy that it gained will be given by 1 electron volt, which comes from the equation E equals QV in book 4. In this way, we may express the energy of a photon of red light to be 1.79 electron volts. More realistic, right? You don't have to use scientific notation anymore. Easier, isn't it? Right, and how about the work function, which is the minimum energy required in order to release an electron from metal surface? The work function is also a very small amount of energy. As you can see, this is talking about 2.1 electron volt, 6.4 electron volt. It's just a few electron volt. So imagine if it is not red light, but violet light, then the energy here will be something like 3 or 4 electron volt. Then the energy of a photon of violet light will be enough to produce photoelectric effect for cesium, sodium, or even calcium, because they have a very small work function. Remember that simulation of photoelectric effect, right? So now I'm using sodium surface, and now I'm changing the color, and just now we said red is not good enough, so let's make it green. And then now I move it to the left towards violet, and when the wavelength is short enough, that means frequency is high enough, then there has photoelectrons emitted. So there need to be a critical wavelength corresponding to a critical frequency. This frequency is called threshold frequency. When the frequency of light is higher than the threshold frequency, then there can be photoelectric effect. So what does that threshold frequency refer to? Well, threshold frequency is the minimum frequency which just gives enough energy to pay off the work function. Simply speaking, the energy of the photon of threshold frequency, HF log, is exactly equals to the work function. Well, on the last page, we were given the work functions of different metal surfaces. So can we find the threshold frequency of platinum, for example? Now you can see this 6.4 electron volt is the work function, and we suppose the threshold frequency will give a energy of photon that is exactly equals to 6.4 electron volt. And in this way, as you can see here, we can easily calculate the threshold frequency of platinum surface. So example 4 is similar. You are asked to find the threshold frequency of sodium. And after that, check whether this wavelength of light may also produce photoelectric effect for sodium. So what has Einstein done to gain a Nobel Prize? What he has done is to give an interpretation, a full theory to explain photoelectric effect. And in his theory, there is an equation, so-called photoelectric equation. It looks like this, which is quite straightforward when we look at this nowadays. So first of all, there is the term HF, which is the energy of the incident photon. Subtract from it the work function of the metal surface, then we may find the energy that is left to become kinetic energy. Now, one thing that you must know is work function is the minimum energy to pay off in order to release an electron and become photoelectron. So, in this way, HF minus psi will then become a maximum kinetic energy. There are some electrons who are quite unlucky that they are not exactly on the surface, but they are a few layers below. And in that way, they have to pay off quite a lot of energy in order to escape from the metal surface. So, the equation helps you to find the maximum kinetic energy of all those photoelectrons emitted. And of course, there are electrons that are emitted and finally have no kinetic energy to move. The equation also allows us to do something. Pick up a pen and copy that down. The equation allows us to plot the graph of maximum kinetic energy versus F. You may know how we may find the maximum kinetic energy of all those photoelectrons by using stopping potential. You may calculate the maximum kinetic energy from the stopping potential, and in this way plot a graph against frequency of incident light. And according to the equation, the graph should have a slope of h. So you may find h this way. The graph should also have a f-intercept of f log, which is threshold frequency. And finally, there is a kinetic energy intercept, which is equal to the negative of the work function of the metal surface. So the graph is important. You must know the physical meanings of those intercepts as well as the slope. Instead of plotting a graph of maximum kinetic energy versus frequency, we may also plot a graph of maximum speed square versus frequency. Quite the same, isn't it? But then in that case, the slope is 2h over me. How did I know this? Because v square comes from v square in this equation. And then f comes from here. And then you may then rearrange the 2 and the me to the left hand side. And then you will see the slope is 2h over me. Since an electron on the metal surface has to absorb energy from just one photon, and then it can be emitted immediately if it gains enough energy. So that's why there's no time delay, because the electron need not collect collect energy from many photons. It just absorbs energy from one photon. If the energy is enough, then it is emitted. And that's why no matter how low the intensity of light is, even if the intensity of light is so low that there are just a few photons falling on the metal surface, then these photons may then already enough to emit electrons from the metal surface immediately when they are absorbed by the electrons. Take a look at example 5 and then try the checkpoint below.